Thanks, Sean. Okay, so welcome to the first webinar of the Net for Cities project. My name is Erica von Schneidmitzer. I am the coordinator of Net for Cities. And I work at the Research Institute for Sustainability in Potsdam, Germany. So thank you all for your interest in this topic and for joining the webinar today. As Sean mentioned, I am going to start by just giving a very brief introduction into the context of Net for Cities. This is a 4-year funded project. It started this year in January with a focus on monitoring networks and transport emissions in European cities. So the main aim of Net for Cities is to help facilitate the realization of the EU Green Deal Zero Pollution Action Plans. And we're going to be doing that by advancing air and noise monitoring infrastructure in cities throughout Europe, and also to provide an evidence base for supporting the effective implementation of transport policies, with obviously the end goal then of improving air quality and mitigating noise pollution across Europe. The context of Net for Cities and this funding is that the Ambient Air Quality Directive was recently in revision for quite a while, and it was adopted last month. And under this revised air quality directive, there are pollutants of emerging concern that should be monitored that are not currently being monitored. And this includes things like ultrafine particles, which will be the focus of our webinar today, as well as ammonia and black carbon. And so that's where the advancement in these monitoring capacities comes in the context of Net for Cities. They also have the action plan towards zero pollution for air, water, and soil, which was adopted in May of 2021. And there they have a vision for 2050 to reduce the levels of these different pollutants to levels that are basically no longer harmful to human health. There's also some interim targets for 2030 for reducing air pollutant exposure and health effects, as well as air pollutant effects on ecosystems and people exposed to chronic noise levels. So they have those interim reduction targets. Emerging pollutants are airborne particles and gases that are harmful to human health that have been increasing in importance and concentration in recent years due to continued urbanization and industrialization. As mentioned, today we're going to be focusing on ultrafine particles, and we're going to be hearing a little bit more in detail about those from some of our speakers. But some of the other things that we'll be looking at in the project include ammonia, black carbon, as well as noise and some of these other pollutants that are listed here, including a few greenhouse gases. We have 11 partner cities in the project, and they are shown on this map here. And that is where we are going to be installing both the CPCs that we will be talking about today, as well as the LDSA devices, as well as noise and traffic instrumentation, although that's not the focus here. And we are focusing on emissions from transport sources. And so you can see associated to the different cities, which transport sources, whether it's traffic, vehicle traffic, ports, ship traffic, or airports, that we are focusing on in the different locations. The main aim of this webinar is to give you an idea of how we're going to be contributing to advancing monitoring in Europe with respect to ultrafine particles, providing a brief overview on UFPs and also how it can be measured, with more specifics provided on CPC measurement instrument and LDSA monitors, and then also allow you to ask some of your own questions of our speakers. So finally, I would like to introduce our speakers. So I've introduced myself. Sean, you heard at the beginning. He's a postdoc in my group and is essential to most things that happen in this project, supporting and coordination. The first speaker will be Aki, who is head of Air Modus, and he's going to provide some background on the revision to the Air Quality Directive, the implications for monitoring, and then also the Air Modus CPC instrument. Following that, we will have presentations from Saskia and Martin to present the LDSA instrument from Nanios, as well as some background on why we might want to measure LDSA, or lung depositable surface area, and then some technical details about the instrument itself as well. So with that, I will pass over to Aki and him take over for the first presentation.
Thank you, Erika. And first of all, thank you for all the partners that are included in this Net4Cities. It has already been really exciting discussions, and I have learned a lot. And this is one of the main things, since now this is a bit new thing for us all, that we get also discussions with the cities and with authorities, and those are kind of the users in the future who will create the network and maintenance the network. So that's why it's kind of a learning process for us also to see how should be the instrumentation in the future, so that it is easy to run and make sure that the data is reliable. So I will talk about the ultrafine particles based on our discussions, and this is something really new. My name is Aki Pajunoja, and as Erika just told, I'm the head of Air Modus. We are now part of a French company called Envea, and I used to be CEO of Air Modus, but now I'm head of Air Modus. Located in Helsinki, so we are working in Helsinki, just next to the University of Helsinki. So here we are. We have new metrics for particulate matter called UFP, ultrafine particles. Atmospheric aerosols, they are really strongly dependent on the location, local and regional sources. So basically they can be really emitted from next to the measurement device. And that is the main challenge regarding the ultrafine particles. Especially those ultrafine particles are really many times they are dominated by the bus which is going next to your measurement station. And that's why it's really difficult or challenge to make any conclusions out of the one site. And that is why we need more and more sites in different kind of locations, and also other data, meaning traffic data. And that's why Net4Cities is a really good idea to make these measurements and create this kind of platform. But yeah, more metrics than just particle mass, concentration is needed, and also strong quality monitoring network in cities is needed to tackle the health effects. I will go through shortly background of the ultrafine particles, particle mass, particle matter, and the PM2.5 and PM10. But basically the traditional PM10 and PM2.5 monitors do not measure particles smaller than 100 nanometer. Some of them, if you rely on OPCs, actually the detection starts from 600 nanometer, and even you get PM2.5, it doesn't mean that you have measured all the mass below 2.5 micrometers. And also the PM2.5 level may seem low many times, but the number of the smallest particles, the ultrafine particles, can be extremely high. And now we have the newest European directive, which is defining the ultrafine particles. And it was just launched October 24. Of course, we already knew that before that this kind of directive is coming, but they are defining the ultrafine particles as particles with diameter less or equal to 100 nanometer, where the UFP particles are measured as the particle number concentration per cubic centimeter for size range with the lower limit of 10 nanometer, but the size range has no restriction on the upper limit. So this can be confusing, and I can tell it is. But this is basically that the ultrafine particles are so much dominated by the particle sizes below 100 nanometer. So basically the UFP tell the concentration below that. But then the technology is limiting, or to make some requirements, really simple requirements for the technology, there comes the 10 nanometer, and the upper limit is not restricted. So this is coming from the actual technology, the condensation particle counting technology that we are using for measuring those ultrafine particles. But the main thing I would say with this directive, I encourage to read it through, but there's no limit for ultrafine particles. There's the measurements will be mandatory, and there's certain definition that there has to be one CPC measuring every 5 million inhabitants, or if it's rural air, it's about the area that every 100,000 cubic square kilometers. But basically, it's not that simple. But basic idea is that if the country there's a lot of people, it's really dense in that wise, then we need to monitor also CPCs. So there's a clear health aspect for as a motivating factor why we are measuring the ultrafine particles. Shortly about the particulate matter ultrafine particle comparing to the PM, the traditional PM values. So PM comes from particulate matter. Typically, it's micrograms per cubic meter. PM10 means that it's a total particle mass of particles of 10 micrometer and smaller. That's the definition. And the unit is micrograms per cubic meter. So it's mass concentration. PM2.5 analogically is mass of particles, or mass concentration of particles smaller than 2.5 micrometers, and PM1, same thing. Ultrafine particles is basically particle number, not the mass. It's a particle number concentration. Particles larger than few nanometers. In EU directive, it's 10 nanometer, but smaller than 2.5 micrometer. So actually, it is not PM 0.1, but because of the technology, but basically the numbers would be quite the same. So that's why many times we are using, when we are speaking, we are using the 100 nanometer definition, that those are the particle number concentration below that. But when we are looking and comparing the particulate mass in mass concentration against particle number concentration, the left hand side you have particulate mass in mass concentration and same in particle number. I'm assuming now that the particles are spherical. They have density of water, which is many cases okay to assume they are. And in this table I am assuming in the first row that if the particle mass is 5 micrograms per cubic meter, and if the particles are just 100 nanometer particles, nothing else, just single size particles, you need to have 10,000 particles almost to have 5 micrometers per cubic meter. But this is already huge number of particles in number, 10,000 particles almost. But if you remain the particle mass concentration same at 5, which is actually really low for ambient, but having only 1 micrometer particles, not smaller, not larger, you need just 10 particles to match the same mass, but the number is totally different already. And then, for example, if you have 5 times more mass concentration, 25, which is one limit in the EU directive for particulate mass concentration, and if you have just 10 micrometer particles, you need to have just kind of a fraction of one particle to have the same mass as 10,000 particles with 100 nanometer in size. Why we are measuring particle number, not mass, is that the smallest sizes, the number is dominating the values. The particulate matter mass-based measurement systems are insensitive for those smallest particles. And then one thing is that if you have mass, you need to know density of the particles, you need to know shape of the particles to make some assumption of the shape or the effective density. And that's why in ambient monitoring, it may be really, really challenging to have average shape factors or density values to calculate the mass. So that's why as the technology for particle number measurements is basically real numbers. There's no calculations in between. That's why maybe that's one of the reasons for background of these number-based measurements. Particle number is not same as particle mass. Basically, in particle number, if we have the typical particle number concentration figure, like in this plot, it starts from somewhere around 1 nanometer where you have individual molecules, and then the first clusters that are stable, that they stay as a particle phase. Those clusters are growing with molecules so that they can be nucleation event, and there the nucleation mode is ranging between 3 to 10 nanometers. These are really rough estimations. Then we have condensation taking place and the particles are growing even more. We have so-called Aitken modes, accumulation modes, and those accumulation mode is many times kind of intermediate states that is visible in mass distribution, but also in number distribution. But when we go even higher sizes, micrometers to 10 micrometer, then basically in number, you don't even see the particles in this kind of figure. But if you change this kind of graph to mass concentration, then you don't see the number, these smallest sizes, but you see only the larger sizes in micrometers. Then about the technology, in this same figure, now I have combined traditional PM sensors or monitors. Now I have selected OPC based, where the lowest cutoff, you see the pink bars here in the figure that indicates the range that those PM10 and PM2.5, PM1 are actually measuring. So depending on the optical particle counter laser wavelength that you are using, you cannot go lower than, let's say, from 300 nanometer to 600 nanometer. And then you get the total particle mass up to 2.5, 10, or 1 micrometer. The CPCs, condensation particle counters, which basically measures individual particles as counts, they are overlapping the 2.5 in number, but of course the unit is different. But basically from CPC, you get the total particle number concentration for the entire range that it is calibrated. The lower limit, we are talking about cutoff size, and then the upper limit, which is basically around 2.5 micrometers. We, in AirModus, we have this traditional A20, A30 CPCs, which fulfill the CEN requirements, the European requirements. And then we have also tuned our A20 to ultrafine, so it starts from 3 nanometer. And then we have also the special tool called particle size magnifier plus CPC, and that combination actually gives the size distribution from 1 nanometer to 12 nanometer. But this is not regulated, so we don't need to talk about that today, but it is really, really good instrument for measuring the smallest sizes, what is happening beyond the regulation, basically. The health effect is basically the reason why we have started to measure ultrafine particles. The PM size, micrometer size particles, they go to nose and throat and the first parts of the lungs, but the smaller the particles gets, deeper they go. And this is the reason. Just a couple of words about the condensation particle counter. This is the basic standard method for measuring ultrafine particles. And this is, I have written also the standard EN 16976. And this is also really fresh from this year, but you can also have a look for that because it is standardizing technology, calibration, inlet, all the corrections, calculations, they are there as an appendix. And the main thing for standardizing these measurements is harmonizing everything so that we could compare CPC to CPC, station to station. If this CPC is telling 4,000, can I compare it to the other location and other CPC? That's why everything is harmonized. Regulations are really strict on, they are really strict, or basically all the measurements that are made based on CEN, this new standard, you can trust that they are comparable. The CPC technology is really simple. How the CPC works? You have inlet, you saturate your working fluid, usually butanol or also propylene glycol. Then you have saturated air. Then you cool the sample. You have condenser, and where the working fluid activate the nanoparticles, you grow them, the nanoparticles, up to large enough so that traditional optical particle counter can count them. And that's basically it. Of course, there's many parts between. We increase the speed so that they really come individually, the particles in the optical particle counter. We do not use any CloudMore or anything, but basically the CPC technology is widely used method. There's no dilution, no charging required. There's really minimal correction factors, and particles are counted individually, one by one. There's no model for any cloud correction or something, but we are measuring single particles one by one. Then about complete UFP measurement setup. The key, as said, is to harmonize the entire setup, not only the CPC technology. What do you need for the UFP measurements? If you are interested in it, you need the CPC, you need the vacuum pump for that. Inlet tubing, it has to be conductive like stainless steel, it has to be laminar. All the calculations are written in the standard, and they are quite easy to check that you can design your own inlet as well. The inlet has to include some kind of PM hat or cyclone, and Nafion dryer to dry the inlet line lower than 40% of relative humidity, and the humidity needs to be monitored in the inlet line. Exhaust tubing for CPC, it's like normal plastic tubing, and then data acquisition system. In our case, we are using different third-party solutions or our own multi-locker, which is included with the CPC. The complete setup is provided by AirModus. Then you are maybe interested in the basic maintenance. What do you need to do on field by yourself, or what it needs to be done for CPC? And filling working fluid is one thing that you need to do it one or once per month or once per 3 months, depending on the CPC model and working fluid. Then the user needs to measure the inlet flow. We prefer once per month with the external flow meter. Service in CEN is preferred to be done once per 2 years, and also calibration, which need to be done in official lab. It has to be done every 2nd year. And then the last slide is the ultrafine particle setup in this project, Net4Cities. You can see the default package in the picture on the right-hand side. It's really compact. That was our aim. That is easy to install. It's compact. It doesn't take so much room from the station. There we have the compact 830 CPC. Vacuum pump is left side of the CPC, so you don't need to have large pumps or so. We are using 12-inch long Nafion dryer in the inlet. That is visible also in the picture. After Nafion dryer, we have Cyclone, mini Cyclone to cut off the large particles or bugs or pollen or something away from the stream. Then we have the RH temperature and pressure monitor just before the CPC inlet. And to make it fully complete system, we have data acquisition system. We use this kind of IoT logger which is connected to cloud. We see the data. We have full remote control for the data all the time, and we have automated alarms and errors. And of course, the standard is also requiring certain diagnostics. All of them are included in this system. Data is 1 Hz as a default. It is hosted by Nilu in this project, and it will be available for all. And the last thing, we also provide the aerosol flow meter for monthly checks. That you can see also in the picture. Thank you for all. And the last thing, we are AirModus, and we are located in Helsinki, but we are now part of NVA Global, which has headquarters in France, and the ultrafine particle instrumentation is developed and will be developed in Helsinki here in our development hub.
Thank you very much, Aki. So just to reiterate, I see some people have started putting questions in the chat. If there are very common questions, we will maybe also answer them in the Q&A in person at the end. Otherwise, some of them will be answered by text. And at this point, I would pass over to Saskia to continue with the presentations.
Yes, hello, thank you. You should be able to see my slide now. So my name is Saskia de Gosset van Disseldorp. I work at the Zurich University for Applied Sciences in the research unit for meteorology, environment, and aviation. I will be presenting some facts or some key concepts and application about long deposited surface area, so LDSA measurements. I will be presenting from a user perspective to give you an idea of why we use it here in Zurich and why it is how it is a very easy experience and an easy device to use. And afterwards, Martin Fritz from Naneos, who are building the measurement devices, will give some more technical information on how the devices work. So some key concepts we just heard very nicely from Aki, why ultrafine particles are not at all the same as PM. So I'm not going to go into that. What LDSA is measuring, though, what's different from the number concentration is the long deposited surface area. This measures the area of airborne particles that are small enough to deposit in the lung, so in the ultrafine particle section. And it is measured in square micrometers per cubic centimeter. So it's an area per volume of air. And the reason why LDSA, so this area, is an interesting thing to measure is, first of all, it's quite easy to measure, as Martin will explain later on. And also, it is a good metric for and a good proxy for the toxicity of the particles and of the nanoparticles. That is due to the fact that the interaction of the particles, so the non-soluble particles that we are talking about, with bodily tissue, so in the lungs and bloodstream even, happens at the particle surface. So the larger the particle surface, the higher this the potential toxicity, and the particle surface is also directly dependent on the size of the particles. So the smaller they are, the larger the surface in relation to the mass of the particles. The measurements are, from the user perspective, again, quite easy to conduct. So the devices, the outdoor devices, are easy to deploy. You can see the picture, the left picture. We see this white box. This is the outdoor casing, so a weatherproof case to mount it outdoors. It's not that big. We will see it afterwards with a person in the picture, so you have an idea of how big it is. They're easy to mount, and it's a plug and play type of instrument. The data transmission is automated, so there's no, it goes via IoT. And as I said already, it's coming in a weatherproof housing, so it can stay outside all year. And then there is an easy to follow maintenance protocol. Maintenance is mostly quality checks to ensure the high quality measurements. Parts of it is done via metadata. I think Martin is going to talk a bit about that automatically, and part of it, or as an addition, there will be, or there are handheld devices that can be seen on the right with the black background. Those are Partector 2 devices. They will be shipped to the partner cities for Net4City as well. And we will see in a bit how to do co-location measurements with those devices to ensure a good quality and high quality measurements. This is a closer look at the devices from the back. So these are the outdoor ones. And you can see on the left, it's a picture of the mounting bracket, or the hanger where the mounting bracket is not attached. On the right, you can see it with the mounting bracket attached. So we will see the next slide that the mounting works really easy. The mounting bracket is attached to a pole or a wall, or where the measurement device will be located, and then it can be hanged with the hangers and fixed with a screw. The inlet and the power plug are also indicated there at the bottom of the instrument. This is a picture as promised with a person. You can see the first picture where the mounting brackets are installed at a pole, and then the devices can be just hanged in. So it's a really easy procedure. So the co-location measurements, as said, are done with this handheld device. They are quite small and handy, and there is a simple protocol. So what happens is that whoever is doing these co-location measurements just places the Partector 2 device next to these outdoor devices or on top of the outdoor devices to measure, to do those co-location measurements for a while, and then fill in the protocol, which contains the start time and end time of these co-location measurements, the weather conditions on site, and some more information if there are any interesting ones. The data analysis of these co-location measurements will be done remotely for the Net4Cities and will be conducted here in-house at ZHW. Now, just one example of the application that we used it for. It's a pilot case from last year, which is not published yet. It's just a peek into the data. So the devices noted here are we placed or relocated a couple of the outdoor devices along a transect where we covered a highway and then one remote station that's close to the airport of Zurich, and then 2 devices in the residential area to compare the long deposited surface area concentration in near or next to different sources. This is, as I said, just a sneak peek. It's the diurnal data averaged, and the top left panel shows this long deposited surface area, and it shows a peak in the morning and a high concentration near the highway, near the road, and the lowest concentration in the residential area and or the garden and farm area. The interesting thing with those measurements, especially when the devices are deployed for a longer period of time, is that they can be compared to other data, so other air quality data, to get information of how they are connected and how they correlate. In this study, we also developed a model, a dispersion model, to see to simulate the source dispersion of those ultrafine particles in terms of long deposited surface area. This was a pilot case. We hope to build on this project and publish the study soon. So that was a peek from the user perspective, and I'll happily forward the word to Martin.
So thank you, Saskia, for that. And I would give a polite reminder to everyone that if you have any questions throughout, please feel free to ask your questions in the Q&A section, and we will answer them either now, during, or at the end. So thank you. Martin, go right ahead. I'm not sure if you're speaking, Martin, but your camera and is off and you are muted. So it'd be great if you could do that. Yeah.
Yes,
thank you.
I'm working on it. So welcome from my side. I'll talk a bit about the sensors that we developed for this project. My name is Martin Viertz. I'm co-founder of Nanios, and we build such instruments, right? So when you think about measuring UFPs, there are many things you can measure. Aki already mentioned you can measure particle mass, you can measure particle number, you can also measure particle size distributions and many other things actually. And the standard devices, we've heard it, are those CPCs of Air Modus or other companies, or you can combine it with a size spectrometer, and then you can measure particle size distributions. And all of this, as Aki also already mentioned, is now being standardized, has been standardized, and we are supposed to use those devices. And That's fine because those are great devices. I'm just making a but here because they are usually operated in monitoring stations, because often those kind of devices are sensitive to environmental conditions. They're also a bit costly and complex. And so that kind of limits the application to, putting them to monitoring station or not monitoring at many different sites. And so the question is, how can we extend the coverage? And of course, it's going to be a trade-off. You will not get the same data anymore, but you can extend the coverage in some way. And the potential alternative, or the thing that I am showing to you here, is something to do with diffusion charging. In diffusion charging, you have a setup which is something like this. So the whole idea is to measure electrical currents. So we have aerosol or gas entering the instrument from the left side, then we have a high voltage zone where we create a discharge and create ions. They will combine with the particles, and then this charged gas stream will flow down towards a filter where you can measure a current. And it's super simple. Maybe it's not quite as easy as it looks, because you need to be able to measure femtoamps. That's kind of little in terms of current. But the big advantage of this sort of thing is you don't need a radioactive source, you don't need a working fluid, it's tolerant to orientation changes, tolerant to temperature changes. So it has some potential to be deployed in locations where you would want to make use of this. Saskia already mentioned that you can interpret the signal as long deposited surface area. If I just go back to kind of the basics, what the current is actually that we measure, it turns out that the larger the particles are, the more current they will take up, or the more charge. And it's more or less linear in particle diameter. So whatever current we're measuring is some calibration constant multiplied by the particle number, multiplied by the average particle diameter at this location. So it's kind of close to the particle number which the CPCs are measuring and which is mandatory to measure, as we heard, but it's kind of modified by this average particle diameter. You can think of it as a length concentration if you wish, as millimeters per cubic centimeter, but I prefer the interpretation as the long deposited surface area. In any case, if you want to stay with a little bit of mathematics, if you think about the CPC measuring particle number, and you would like to go to particle mass, you would have to multiply with diameter to the power of 3, because that's the volume of the particles. So this is actually closer to particle number than particle mass. So you can still see the ultrafine particles. And on the right, you can also see that you can still measure down to about 10 nanometers. Smaller particles, you won't be able to measure. That's when you then really would need a CPC. So as Saskia mentioned, we built a couple of such stations for outdoor monitoring 4 years ago, and ZHAW has been using those for about 3-year period for measurements outdoors. And even though they were very quickly made prototypes, they were kind of good. They worked really well. And it encouraged us to make a new version for this project. So the new version is brand new, it's improved. But obviously, because it is brand new, there is some potential for problems which we haven't seen yet. So the sensor unit itself is in a protective housing. You can see it's kind of small. You can see this pen here. And the whole sensor unit then comes in a white box. And you can mount this basically anywhere. So it doesn't need to be controlled in any form. There's no drying needed or anything. The way we do this is there's a heater included. So if the ambient air is too humid, we just heat up the inlet air to make it a bit less humid inside. And we can also prevent low temperatures in the box this way. We also have a very white box, so it will reflect the sunlight and not heat up in the sunlight. Okay, so the operating conditions for the sensor, we don't know exactly yet, but probably it's about 0 to 50 degrees Celsius for the sensor unit itself, so inside this box. And Of course, you can have ambient temperatures below 0 degrees, but then our heater will prevent the sensor from becoming too cold, and hopefully it will not be hotter than 50 degrees. Because the whole thing is going to be deployed in the urban environment, you need to try and prevent tampering, so the box can be locked with a padlock. It does need 230-volt power because of this heating thing. We provide cables, 5 meters with the correct plugs for each partner, but if you need more than 5 meters, you will have to extend it yourself. And as soon as you plug in the box, it will start transmitting data automatically. So you don't need to do anything. You don't even need to open the box. You just plug it in and it starts working. It will transmit data to us exactly like as Aki explained for the CPCs. So it will be transmitting by the mobile phone network, and we will see the data, the LDSA data, and also status data. We will get alarms. We will get, we can monitor the health state automatically. So if anything is out of order, we will inform you immediately as soon as there's a problem. There's a maintenance planned for mid-project. After 18 months, then all devices should be returned to us for a service. And that's about it. The quality control, to last but not least, Saskia mentioned, we have this other instrument to make a simultaneous measurement and cross-check whether the boxes are working properly. So you get this handheld device. And this device, I must admit, was never designed for 24/7 operation long-term like the new instrument is. So if you get this device and use it, then please don't use it for crazy stuff, because it will not tolerate like 24/7 operation for 3 years. It will not tolerate. Probably it will also not tolerate measuring vehicle exhaust directly and other things. So please handle with care so that it can really serve as a reference instrument. Okay, that's it from my side, and I hope we still have some time for questions.
Thank you, Martin. Yeah, so we have about 10 minutes left in the webinar now. You can feel free to put your questions in the chat. There were already a couple of questions in there that have been answered. If you have looked at the Q&A, you will hopefully see that there are different tabs you need to click on at the top to look at the answers to the questions, because there are different tabs for open question, answered questions, and dismissed questions. So maybe just briefly, there was a question about service and cleaning of the cyclones, where Aki provided an answer. And basically, it's as necessary, but he recommends cleaning it a little bit more often if it's an area where there are higher concentrations, and otherwise less so if it's in a cleaner environment, but that there are also diagnostics that will flag inlet pressure. Martin, do you want to answer that question live?
Yeah, there's a question straight for you, Martin, if you would like.
Yeah, I can answer
Perfect.
that directly. So, we don't have to heat a lot. So if you have 100% humidity in the ambient air, then you just need a few degrees of Celsius, which you increase the temperature so that you're down to about 70% humidity, and then that is sufficient. So it's not like we're heating to 10 or no, to 100 degrees or anything. I also see there's a question of the average diameter. It's not determined. It's a LDSA measurement only. It's integrated in the device. That's just the charge that is acquired that is going to be proportional to average diameter multiplied by particle number. So you cannot determine this in the LDSA measurement itself.
Thanks, Martin. There was also the question about how much power the devices need. If you wanted either Aki and or Martin wanted to answer that. Well, it looks like it was answered in the chat.
Yeah, I wrote it already there so that people can take it from there. But yeah, and that is including everything, so all the pumps, vacuum pumps and CPC. But basically CPC cannot be run with battery or with solar panel. The consumption is so high.
Yeah. Yeah. Maybe you also want to just comment briefly on the working fluid. I know you answered it in the chat, but yeah.
Yeah, regarding the working fluid, so the traditional working fluid is butanol, but there's many downsides with the butanol, and that's why there's now a lot of research on different working fluids, and our choice has been the propylene glycol. There's a recent publication about the comparison performance between butanol and propylene glycol. In addition, we have had the comparison measurements in an ambient monitoring site, and we are continuing that. But the propylene glycol is much cheaper. The consumption is much lower. So basically, with half a liter bottle, you can run a 30 CPC almost a year. So the cost is 20 euros comparing to a 20 CPC with butanol. It's around 800 euros a year, the butanol only for 1 CPC. So the consumption is totally different. And that's why those are the things that why we are using now in Net4Cities, we are using propylene glycol. Also the cross sensitivity. We know that there's a sensitivity of the benzene monitors, for example, to butanol, and that's why we want to avoid that. But of course, in some cases, butanol CPCs are in use. In Net4Cities also, there's also older CPCs that are there already, and those are, of course, using mostly butanol. But the water is not the choice in our project because it's so sensitive to particle composition. That is shown before in the publication, so that's why we are using alcohol-based method.
Thank you. Okay, so I think then we have answered all of the open questions. We'll keep an eye on the chat for the Q&A for the next 5 minutes in case anybody wants to ask any other questions or is currently typing. But before we go, I would also just like to thank all of the participants again, especially those from our partner cities. We are very thankful for your collaboration and commitment to this project. And we look forward to getting these devices online and delivering data. And as Aki mentioned, that data will be publicly available through the Net4Cities Data Hub, which is being run by NILU.
Maybe to add to that as well, just very briefly, our timeline in the Net4Cities project is to have our instruments, including the CPCs and the LDSA instruments that you saw today, to be online and available as of March of next year. And the plan is for these to be a minimum of 2-year-long data sets running through the end of 2027. So with these long-term data sets that are available to all, we will learn hopefully quite a bit about UFP from transport emissions specifically in all of our different partner cities. So keep tuned, stay tuned, so to say, for all of the results to come in our project. But as Erica mentioned, thank you so much for your participation today. And as we're saying goodbye, I see there's one more question that just showed up. So perhaps we can answer that right now. If Martin or Aki, if you know what the longest data sets are for these instruments.
Martin, did you see the question? The longest data set so far from the instruments, particularly for the LDSA. I'm wondering about long-term stability and reliability of the technology.
Yeah, so as I mentioned, the instruments that we already built, that Saskia and her colleagues have been operating, they have been working for 3 years in total. So we built them 4 years ago, and we had some service pauses in between sometimes, but the total operation time was 3 years. And the last deployment was, I think, a bit more than 1 year without touching them. And they were quite stable, except for one which was damaged in a thunderstorm. Well, that's what you get if you put them outside of the station. So we are, I mean, to be honest, we are also wondering about long-term stability and reliability. We believe this is going to be really stable, but obviously we will find out more.
Yeah, the first Air Modus CPC, butanol-based CPC, was installed basically 2012 or something, so 12 years ago, and there has been continuous measurement, ambient monitoring measurements with PSM or without. So those are the starting points for the long measurements. The CPC technology itself is a really old method, and that is why basically it is also in the standard. But the propylene glycol is new thing. There's only months continuous data sets, and those are kind of research data sets. So the CPC has been tested at lab in between, and that is also why Net4Cities is really perfect. All the CPCs are in our control, so we can anytime test it, compare it. How is the long-term usage? So this open kind of, this is a validation, I would say, also for the whole community, and hopefully we can get some conclusions out of this for the standardization group as well.
Okay. Then, if there are no further questions, we would thank you all again for your participation and end the webinar.